also move on to the next talk. The next paper, which will be a recording, is titled On the Joint Control of Multiple Building Systems with Reinforcement Learning. The presenter is Tianyu Zhang from the University of Alberta. And a very short bio, Tianyu Zhang is a PhD candidate at the University of Alberta. His research interests are in sensor networks, building controls and modeling, and reinforcement learning. Okay, over to you, Ram, if you can play the video, please.
Yes, so Sydney will be playing the video. There you go.
Hello, everyone. I'm Tianyu Zhang from the University of Alberta. Today, I present a study called The Joint Control of Multiple Building Systems.
Can you pause it once? There is an overlay window on the top of the video. Can you move it below or just close it?
Is the overlay part of the recording, Ram, perhaps?
No, I've not seen that in the recording, no. Or can you try just sharing the applications with me? Not the entire screen. Or perhaps the other way around. If you're sharing the application already, try to share the entire screen.
Okay. Is it okay now?
I still can see that. Okay, let me share the screen then. I have the video, so I'll take it over, Sydney. Thank you.
Okay.
Yeah. Arun, you can see this, okay?
Yes, I can.
Hello, everyone. I'm Tianyu Zhang from the University of Alberta. Today, I present a study called On the Joint Control of Multiple Building Systems with Reinforcement Learning. This is joint work with my supervisor, Omid, Ardakanian, and Gaby and Rolf from the University of Victoria. So, let's start with the motivation of this work. Increasing energy efficiency has long been a topic in modern studies, helping to conserve the planet and save money. We can conclude the energy consumption into 4 sectors: residential, commercial, industrial, and transportation. Commercial sector used 12% energy in the United States in 2020. If we break down this 12% commercial buildings' energy consumption by end use, heating, ventilation, and air conditioning system, or HVAC system, and lighting system together consume 40% of commercial sector total energy in the US. For even colder or hotter countries, this percentage will become even higher. For example, if we investigate Canada, a country with colder climate, HVAC and lighting system consumes 79.1% of total energy use in commercial buildings. Therefore, we need a solution to reduce the energy used by HVAC and lighting systems while maintaining the occupant's thermal and visual comfort. To achieve this goal, we jointly control the HVAC system's supply air temperature and blind angle set points using model-free IR agents with and without rule-based out-dimming control of lights in a 5-zone test building in 2 seasons with 2 resolutions of occupancy information. Our results show that compared to baseline approaches, we can further save 11% in winter and 31.8% in summer on electricity consumption when zone-level occupancy information is available using IO agents. Now, in the rest of this talk, I will explain the study in detail. I will start with the challenges of this work, explaining why a model-free approach is preferred and the gap in previous work. Then I will describe the RL problem formulation, control scenarios, baselines, and agents used in this study. After that, I will discuss our experiment results, and finally talk about main takeaways of this talk and avenues for future work. First, let's investigate why this work is non-trivial. In this work, 3 systems can be controlled: the blinds, HVAC, and lights. The goal of controlling these systems is to minimize the electricity consumption while maintaining the indoor temperature and brightness in a comfortable range to fulfill occupants' thermal and visual comfort. But the interactions of these systems are complex. For example, if we open the blinds, the indoor temperature will go up due to the solar radiation. The indoor brightness will go up as the natural light comes in. These effects then make other building systems react. For example, in the summer season, the HVAC might need to do extra works to balance the solar radiation by cooling down the building. For lighting system, since there are some natural light, we can dim the artificial light to save electricity. Therefore, it is not easy to optimize all objectives at the same time. This makes the joint control of the building non-trivial. Another essential aspect that needs to be considered is occupancy resolution. This is because most building systems are trying to serve the occupants of the building. Systems may act differently if the resolution of occupancy information differs. Let's illustrate the impact of varying spatial resolution of occupancy data in a 4-zone building, where we deploy a keycard entry to gather the building level occupancy information, and install some occupancy sensor in each zone to collect zone level occupancy information. Suppose we have 3 occupants in the building right now, and the HVAC system is operating. Suppose only the building level occupancy information is available. In this case, the HVAC system needs to condition the whole building because the system only knows some occupants are somewhere in the building. Although we do not need many sensors to deploy, the cost for HVAC system to operate is high. However, if zone level occupancy information is available, the HVAC system only needs to condition the occupied zones. Although more sensor is required, the energy for HVAC is saved. There are many attempts to optimize building systems. Rule-based and model-based approaches mainly focus on one system, such as HVAC only or lighting system only. This is due to the complexity of optimizing the joint operations we just discussed previously. Model-free approaches provide the opportunity for trial and error learning using data collected in actual or simulated environments. However, most studies focus on joint control in one zone only, and they lack discussion on the trade-offs between electricity saving, thermal comfort, and visual comfort. In this study, we studied the joint control on a 5-zone building with a discussion on how facilities managers can trade electricity savings for extra comfort, or vice versa. We also test our algorithms with 2 different occupancy resolutions and found noticeable differences. Moreover, previous studies usually lack an explanation of why the algorithm is selected. We tested a couple of representative reinforcement learning algorithms in this work. Lastly, the baselines are not the same in previous studies. Some studies compare their method with some baselines that are not strong enough. In this paper, we test multiple rule-based baselines and use the best one as our baseline. One natural question is why we use model-free reinforcement learning. As we described, this is an optimal control problem with multiple competing objectives concerning the operation of building systems with complex dynamics. Model such complexity is costly. Therefore, we solve the problem using model-free reinforcement learning to learn the control policy without modeling the complex dynamics. Now, I describe the Markov decision process framework. We define our environment as a 5-zone medium office building. The left figure shows the layout of the building studied in this work, including the daylighting reference points. As we can see in this figure, we have 4 zones that contains a window, and for the larger zone, Zone 1 and Zone 3, we used 2 daylighting reference points to calculate the indoor brightness. These reference points are located at desk height. Moreover, figures on the right show the 2 occupancy information we used in this study. The top one shows the zone level occupancy information, which determines the number of occupants present in each zone at any given time. Bottom one shows the building level occupancy information. The building level occupancy information assumes that all zones are occupied during the working hour. This figure shows the design of the HVAC system used in our building. It consists of a centralized air handling unit that moves conditioned air through the building via a duct system. In the air handling unit, the outside air and the return air from zones are mixed together. The mixed air is then heated or cooled using one heating coil and one cooling coil to a specified temperature before it is pushed through the duct system by a fan. Variable air volume, or VAV systems, are used for controlling the amount of supply air by opening and closing a damper. A reheat coil present in the VAV box to heat the supply air in the zone to the desired temperature. This allows each zone to have its own thermostat with a unique temperature preference. These VAV set points are controlled using a feedback control strategy, and the VAV reheat coils are turned off in the cooling season. In this work, our RL agents control the supply air temperature constrained by the mixed air temperature, and the angle of each blind at each temp step in each zone that have windows. The state consists of the temperature in each zone, the number of occupants in each zone. Notice that for building level occupancy schedule, all zones share the same value of 0 or 1, indicating whether the building is occupied, the hour of the day, the slight angle of the blinds in each of the 4 zones that have windows, the ambient temperature, and the set solar radiation. In addition to these observations, it contains the weather forecast, which includes ambient temperature and set solar radiation for the next 3 hours. For this study, the forecast is assumed to be perfect. The reward to maximize is a weighted sum of 3 objectives: electricity consumption, thermal comfort, and visual comfort. The weights row represent the relative importance of different objectives. E is the total electricity consumed by the HVAC and lights. TC is the thermal discomfort according to the predicted mean vote, or PMV, specified by Funger's model, where the absolute value of PMV close to 0 is representing thermal neutrality, and the thermal comfort threshold defined by Ashley. We ignore the unoccupied zones in the calculation. VC is the visual discomfort according to the mean illuminance in each occupied zone and the comfort threshold defined by Ashley. To test how the joint control of building systems affect the performance of RL agents, we train all agents in 6 specific scenarios for controlling HVAC, blind, and lighting, where we can assume the blinds are always open, or using the same set point for all blinds, or using different set points for each blind. The light can dim itself or not when the indoor brightness is high. For baselines, we consider 4 different scenarios, where we use the rule-based controller to control the HVAC system only, or with one of the blinds or lighting system, or both. The rule-based controller for the HVAC system uses the estimated heating and cooling load to determine the best set point. This is used to make fair comparison with RL agents. The lights can dim continuously when the indoor brightness is too high, and the blinds are controlled with several rules, such as close the blind when outside is too cold or the solar radiation is too high. To select the most appropriate RL algorithms, we use the most representative algorithm in 3 most common RL fields, which are the branching dueling queue network, a value-based approach, proximal policy optimization, a policy-based algorithm, and an in-between actor-critic method called soft actor-critic. Value-based model-free RL agent keeps estimating the expected reward for each action given the state, using the expected reward to select the action that can maximize the reward. This means we do not have an explicit policy. In general settings, the action is one dimension. In our work, we need to control 5 set points, so we used branching dueling queue network, where we have 5 branches for the last layer. Each branch is responsible for possible action values for 1 set point. Policy gradient model-free RL agent model and update the policy directly without the value function adopted in value-based approach. In our work, we used proximal policy optimization, which limits the step size alpha to a trust region so that the agent can update the policy faster. Similar to BDQN, we have 5 branches in PPO for each set point. Actor-critic model-free RL agent estimates the value function or Q function of the current policy and then use it to improve policy. We used soft actor-critic in this study, which maximized both the expected reward and the entropy, allowing the agent to explore more widely and simultaneously consider multiple near-optimal policies. Our SAC agent also have 5 branches for actions. Now, I will present the results from our experiments. Our experiments are performed using COPS, Comprehensive Building Simulator. For the time being, I will just introduce 4 research questions that we explored in this study in the presentation. Please refer to our paper for more detail. The first question we investigated is how the joint control of building systems affect the whole building electricity use. We evaluate the performance of baselines in different control scenarios in a different season, as shown in the right table. And we conclude that controlling the blinds can save over 10% electricity in both seasons. Adding a dimming control can save over 25% in summer, but won't help in winter. And controlling both blinds and lights can have the biggest savings compared to other control scenarios. We can achieve over 18% electricity savings in winter and 32% in summer. We are also interested in the trade-offs between electricity use, thermal comfort, and visual comfort. These plots show the trade-offs between electricity use and thermal comfort offered by the RL agents in 6 different control scenarios using the building level occupancy schedule. In these plots, the x-axis shows the monthly electricity consumption, and the y-axis shows the thermal comfort violation rate calculated by the thermal discomfort TC. Each circle represents a specific reward parameter setting, and the red dots are the parental optimal values. Black stars are the baseline performance. Black dashed lines are the thermal comfort threshold defined by ASHRAE. Because the PPO result spreads widely in Figure A, the access limits for PPO are different from other algorithms. We used hatched-filled orange rectangles to indicate the access limits of the other 2 algorithms on PPO plots. All dots below the black dashed lines are considered acceptable reward parameters because they meet the thermal requirements. These plots show that the PPO algorithm is sensitive to the reward parameter settings compared to other 2 algorithms because the circle spreads widely in PPO plots. We can conclude that all agents can navigate the 3-way trade-offs by tweaking the reward parameters. The third question we are interested in is the impact of using different occupancy resolutions. These 2 figures show the whole building electricity use in heating seasons along with the thermal comfort violation rate when the RL agents incorporate building level occupancy information in Figure C and zone level occupancy information in Figure D. Better trade-offs can be seen in Figure D when the control agents incorporate zone level occupancy information, because the circles below the black dash threshold are tend to stay on the left of black star baselines. The zone level occupancy information allows the control agents to meet thermal and visual comfort requirements by conditioning only a subset of zones that are occupied. This reduces the electricity consumption by 6.24 megawatt-hour in HVAC and lighting systems yearly, or $437. Another important observation is that the RL agents cannot consistently beat the rule-based baselines when they rely on building-level occupancy information, as shown in Figure C. The fourth question is, which RL agent performs the best? Left figure illustrates the total reward accumulated in each episode when RL agents control the supply air temperature set point and 4 blind set points, and lights are out-dimmed. This is the result in the cooling season with zone level occupancy information and a specific reward parameter setting where the weight for electricity is 1, the weight for thermal comfort is 1, and the weight for visual comfort is 0.4. However, we witnessed similar convergence behavior for other reward parameter settings, months, and occupancy schedules. The 3 RL agents are trained for 400 months and then tested for 200 months in our simulated building. The episode reward is averaged across 10 runs with different random seeds. The shaded region around the average episode reward shows the 95% confidence interval. From this figure, it is evident that BDQN converges to the highest reward, followed by SAC. Looking at the convergence speed, PPO converges the fastest at around 30 episodes. SAC converges slightly faster than BDQN. If we focus on the shaded region, SAC and BDQN agents show more stable performance because of a narrower confidence interval compared to PPO agent. They have better sample complexity and can effectively use experiences from previous episodes to update the policy. The right figure shows the electricity consumption using the zone level occupancy schedule under 6 different control scenarios. The plot for January indicates that SAC, or the pink bar, outperforms other algorithms in the heating season with regard to electricity savings in all scenarios. The plot for July indicates that PPO, or green bar, achieves the best electricity savings. Under all circumstances, the RL agents can save more electricity than rule-based baselines because all bars are shorter than the right bar. Considering thermal comfort shown on the left figure, recall the threshold for thermal comfort violation rate is 10%. If we focus on July, PPO, or the green bar, cannot satisfy the thermal comfort in the cooling season for most cases. The average thermal comfort violation rate is 10.8% for PPO. In contrast, SAC, or the pink bar, exceeds the threshold only once, and the BDQN, or the orange bar, can always maintain the thermal violation rate under the threshold. Right figure shows the visual comfort violation rate of different RL agents and baselines. For the top 2 cases, because the blinds are always open, so we cannot control the angle, the violation rate for all agents and baselines are the same. In all other cases in both seasons, the RL agents can significantly reduce the violation rate compared to rule-based baselines. As the requirements might differ from case to case, there is no clear winner among these 3 RL agents, but we can get a hint of what agents to pick if we have different objectives. In conclusion, there are 5 takeaways from this presentation. We showed joint control using RL agents can reduce the total electricity consumption in both seasons by over 11%. We justified the cost and effort to install occupancy sensor in each zones. We found that fine-grained occupancy information can boost the performance of model-free RL agents and can help RL agents to beat the baseline. We noticed the PPO agent is sensitive to the reward parameters. The SAC and the BDQN agents can typically find better policies with a longer training time. Lastly, we showed that facilities managers can trade electricity savings for extra comfort and vice versa by tweaking the reward parameters once when defining the control agent. For future works, we plan to discuss how to deploy multiple RL agents to control building systems, and also interested in investigating the latent control space that can be derived from multiple buildings, so we can transfer the control agent trained in one building to another different building with affordable performance loss. With that, I conclude the talk and open to any questions. Thank you for your listening.
Okay, thank you. Are any of the authors online by any chance to take some questions? I don't think so. So there were, maybe we have some couple of minutes for a quick discussion if possible. I do see that Keshav has slacked a few questions. And I think that was the first thing we were thinking of too, Keshav. They did try an MPC control, and if not, why not? Any comments on that? Is that perhaps the most obvious thing to have first tried before getting into the model-free approach?
I mean, in my opinion, MPC is sort of the basis for building control, especially given that they have a 3-hour forecast horizon, perfect knowledge that they've assumed. So it seems curious that they didn't use MPC. And secondly, when they say rule-based control, obviously the quality of the results depends on the quality of the rules. So it's pretty much undefined what rule-based control means. So unfortunately, we can't ask the authors that. I mean, and the other question I have, which I said put on Slack, is that, obviously, typically each vendor is going to have their own control system. So you have the blinds vendor, the HVAC vendor, etc. And one of the biggest problems in building control is the fact that these are heterogeneous. And so I don't see how they can do a joint control in the presence of multiple vendors. But I mean, given the fact that the authors are here, I suppose we just have to wait and see what the answer is on Slack.
Yeah. Great. I mean, I just had one other point, perhaps just for a quick discussion, is they do adjust the supply air temperature at the air side. And often the adjustment of the supply air temperature set point, it takes a while for the actual supply air to achieve that particular set point, maybe orders of minutes. And there's also a dead band around plus or minus whatever tolerance they have in that set point temperature setting. So I'm just wondering whether that was factored in their agent. Because one of the things that I have seen is that even that slight time it takes to control can also lead to thermal discomfort, and people can, in some sense, say it's not the right ballpark. So anyway, that was one point I had. I had a few more questions, but perhaps we will just post it on Slack and see what the authors respond, including how realistic it would be to do an experiment in a real building using some of these strategies.
Yeah, I think more generally, since we don't have the authors here, one point for discussion, at least understanding, is the fact that we're forced to do these experiments on simulators, and so any discrepancies between the simulator and the real world are invisible to us. So these results have to be taken sort of with a understanding that there's an error bar which we don't know how to get it.
Yeah. Okay. Okay. So then perhaps we'll move on to the